A turbo machine, alternatively known as a dynamic fluid machine, refers to a device that utilizes the exchanged flow energy between a flowing fluid and a rotating element due to a specific dynamic action. The result is a change in the movement of the fluid and/or a shift in pressure within the machine. On a simplified scale, a turbo machine is made up of a rotor made up of blades or vanes with fluid and rotating element exchange energy, and a shaft that transfers the resulting energy into or out of the system, depending on the type of machine. Because they are reasonably efficient and have relatively few moving parts, they can be applied in many aspects of our daily life. Turbo machines can fall under two categories, depending on which direction the generated power is transmitted. When work is done on the fluid to change its momentum and increase its pressure, it's called a pump. Pumps are power-absorbing turbo machines that convert mechanical energy into fluid energy. Shaft torque is exerted by something like a motor and forces the fluid to move, which results in the flowing motion that we commonly associate with pumping. Gas station pumps and aquarium filtration devices are common applications of pumps that we see in everyday life. The term pump is applicable to all pumping machines, which extends its application to fans, blowers, and compressors as well, which is why propellers on airplanes or ships and automobile compressors responsible for cooling your car also utilize a pump. A turbine, on the other hand, is a power-generating turbo machine that converts the fluid energy derived from fluid momentum and pressure into mechanical energy. In this case, the fluid does work on the turbine, but by forcing rotation and producing shaft energy. Gas turbine engines on aircrafts and power drills used by dentists both utilize turbines as their source of power generation. As discussed earlier, turbines can operate with a number of different working fluids, most notably gas, steam, and water. Hydraulic turbines utilize water as the working fluid by converting the kinetic and potential energy of water into mechanical work, and are most often used for electrical power generation. The two most basic types of hydraulic turbines are impulse and reaction hydraulic turbines. Impulse turbines generate the force needed to move the blades solely by turning the fluid without a pressure drop in the blade passage. They also operate most efficiently with lower flow rates. The dentist drills mentioned earlier in this presentation are typically of the impulse class. Reaction turbines, however, generate forces with a combination of fluid turning and the force resulting from the acceleration of the fluid relative to the blades. They operate most efficiently with high flow rates, which is why wind power mills are typically of the impulse class.
The textbook classifies three different types of turbo machines: axial flow, mixed flow, and radial flow. The first type we will discuss is an axial flow. An axial flow compressor is a type of turbine in which the flow enters and exits the compressor in the axial direction. This type of compressor works by accelerating a fluid into the turbine and diffusing it, which results in an increase in pressure. Relating axial flow to examples we have studied in this class, airfoils contain the foundation of the theory behind the flow in an axial compressor. The aim of this model is to maximize the pressure ratio. The figure on the bottom shows the velocity gradient of the axial flowing rotor blades. An axial flow compressor is most commonly seen in jet engine applications due to its high efficiency and mass flow rate. One of the most beautiful engineering masterpieces is the Lockheed SR-71 Blackbird, powered by the Pratt & Whitney J58 P4 engine. The Blackbird is the fastest aircraft in the world and can reach speeds up to Mach 3.3, which is a little bit more than 2,000 miles per hour. We will be examining this aircraft specifically because it is equipped with a two-stage axial flow turbine, which is instrumental in the success of the aircraft. The axial flow has a large mass flow rate and a high efficiency. For our discussion, these two factors correlate to a higher thrust and a better fuel efficiency. In this video, we have a demonstration of how the axial flow operates in a jet engine. First, air goes into the cord that compresses the air until it is mixed with jet fuel. At this stage, the air and fuel combust and gets rushed to the back of the engine into the turbine. The turbine shown collects energy from the heated air that came from the combustor and is expanded out the back to produce thrust. Most of the power from the turbine is used to spin the fan blades. We can also see there that there are multiple axial stage blade groupings. As the first set of blade rotates, the blade strikes the fuel, which forces it to the back of the engine and compresses it. This generates a flow along the axis, hence the name axial flow.
Another type of flow is radial flow. So for this kind of flow in machines, the flow across the blades typically involves a radial flow component either at the rotor inlet or at the outlet, or sometimes both. The typical mechanisms for radial flow machines can be mirrored by Euler's equations. So Euler's turbo-machine equation, sometimes called the Euler's pump equation, plays a central role in turbomachinery. And it connects the work and the geometry and velocities in an impeller. It's based on the basic principles of conservation of angular momentum and conservation of energy. So the Euler's turbo-machine equations are shaft torque, which you can see the equation listed, water horsepower, and pump head. R1 and R2 are the diameters of the impeller at the inlet and outlet. U1 and U2 are the absolute velocities of the impeller at the inlet and outlet, and VT1 and VT2 are the tangential velocities of the flow at the inlet and outlet. So these equations can just predict the impact of changing the impeller geometry on the head, and it doesn't really matter if we deal with a pump or a turbine. If torque and the angular velocities are like a sine, work is being done on the fluid, and then if they're opposite, then work is being extracted. So the Euler's equations prove to be very useful. A very common aspect of radial flow turbo machines is a centrifugal pump, and this type of pump has, again, two main components: an impeller attached to a rotating shaft and a stationary casing enclosing the impeller. So the impeller consists of number of blades, and sometimes they call these vanes, and they're arranged in regular pattern around the shaft. And so as the impeller rotates, the fluid sucked through the eye of the casing and the flow is radially outward.
The next flow type that we'll be discussing is mixed flow. This includes both Francis turbine and mixed flow pumps, and it combines the aspects of radial and axial flow by making the fluid enter radially and exit axially. The Francis turbine's primary function is to reduce the velocity of discharged water to minimize the loss of kinetic energy at the outlet. So the reason why this turbine is the most commonly used type of hydro turbine, making up about 60% of the global hydropower capacity, is due to its wide set of conditions that it needs in the head and flow rate. So it could take a head of 45 through 400 meters and a flow rate of 10 through 700 meters cubed per second, which is very broad. So the runner is the most important part, and it's what makes it rotate. How it works is it has blades inside of it, and each blade is designed so that there's high pressure on one side and low pressure on the other side, producing a lift force. And this, along with the impulse force from the water leaving axially, causes the rotation and the energy produced. In the picture below, we have the Euler turbine equation, where we could calculate the torque and power force based on the following picture. The mixed flow pump is a pump that's commonly used in the water industry when transporting contaminated water or water with suspended solids. So the way it works is using a pressure deficit and the vacuum created by the impeller, the water can be brought up to its desired location. So as the impeller spins, the water starts rising, and it moves radially through the inclined blades and axially through the guide blades, and then it reaches its final destination.